All right, so today we are doing a crash review on quantum numbers and electron configuration. Do y'all remember what those were? Yeah, they're good stuff, good times, easy stuff. Most people had no trouble with those topics, and I'm a little tangled here. Excuse me, audience at home, trying to untangle myself. Okay, so where this whole idea of quantum came about was after Bohr and his whole orbital model. So remember the middle school model where you have the nucleus and then the circular orbitals? Yeah, in theory that works, maybe for hydrogen, okay? But first of all, it's not a two-dimensional thing, and secondly, we cannot predict the path of an electron as closely as it's kind of assuming we are with this model. And so that's when Heisenberg came along and decided that rather than looking at an orbital as just a simple path, we have to look at it more like just an area of space where we're probably going to find an electron. And so Heisenberg uncertainty principle suggests that there is a limit as to how precisely it's possible to know both the position and the energy of an electron. There's this joke where this electron, and I'm going to mess this up, I always do, was pulled over by the police for speeding, and the cop was like, do you know how fast you were going? And the electron's like, well, no, but you know where I am, or something like that. It's not even funny. Anyway, you can't know how fast and the location of an electron at the same time. That's kind of what the electron driving the car was alluding to. But anyway, we're going to look at the electron as moving around in an area of space we call it an electron cloud. And that's just a place we're going to find a high probability of locating an electron. All right? So, with that being said, we introduced the idea of Schrödinger. So Schrödinger was like working along with Heisenberg's theories and came up with this really big equation. And it's a P-Chem graduate school type of a scenario where the actual solutions to the equation are going to be the quantum numbers that you guys learned in regular and in pre-AP. The quantum numbers, I like teaching them not because I expect you to know the equation or all the craziness, but it's a really cool way of organizing electrons, and it's kind of the basis of the entire periodic table. It's how it all is put together. It's pretty, to me, pretty amazing. It's what I call sexy. So it's very sexy. Quantum numbers are awesome. So moving on, let's go ahead and review a little bit about our orbitals before I jump into quantum numbers. What are our four orbital types that we deal with? S, spherical, okay, again, three-dimensional. It's like a tennis ball. It's not really a tennis ball, but it's a three-dimensional sphere. You've got your P's that are dumbbells, and there's how many P's in one set? Three, good. There's PX, PY, and PZ, and they're all p orbitals. They're just going in different directions. So X is actually up and down, Y is like X, I can't even speak. X is up and down, Y is across, and then the Z is pointing straight at you if you're putting them all overlapping them in a plane. D's we're not going to draw. They're the weird, there's 5 of them, and they're clover shaped. Some of them are like this dumbbell with a donut around them. They're all crazy shapes, and they have funny names like dxy, and there's one called dx squared minus y squared, crazy stuff. All you need to know is that there is one S on a sublevel, 3 P's on a sublevel, 5 D's on a sublevel, and how many F's? 7 F's. That's it. If we have time at the end, I'll show you some pictures. If not, your textbook is laden with all sorts of those kinds of pictures. That's why you should be reading, so you can get additional knowledge from textbooks. Okay? So let's go and relate this all to quantum numbers. There are 4 quantum numbers. The principal quantum number, which is indicated with an N. The azimuthal, which is an L. The magnetic quantum number, whoops. There it is. The magnetic quantum number, which is an M sub L. And then the spin quantum number, which is an M sub S. What all of those things combined do is bring you to locate and narrow down the location of an electron. So I like to think of it as trying to find somebody. Let's pretend I am hiding from you because I don't want to be a teacher anymore. And all of you go to New York City to try to find me. And you find out I'm in the Waldorf Astoria Hotel. And God, that sounds really nice. And I'm there, and you needed to locate me. What's the first thing you're going to do to find me? Find what? The floor. So that's equivalent to the n, to the level. What level I'm on. Okay? What energy level. And on the periodic table, that's row 1, row 2, and so on. Now, what's really nice about the Waldorf Astoria, there's different sized hotel rooms. There's your 1-bedroom, your 3-bedroom, your 5-bedroom, and your 7-bedroom. They really do call them 1, 3, 1, 3, 5, 7. Okay, so wouldn't it be kind of nice to know what condo, which hotel room I was in? So that's what the second quantum number does. That is the azimuthal quantum number, and it tells you what sub-level the electron's in, what S, P, D, or F. So am I living large in the 7-bedroom, or am I just chilling in the 1-bedroom? Okay. And then you're going to keep looking for me, and once you get into the right hotel room, what will be the next question? Which bedroom I'm in. If I'm in the 1-bedroom, well, I'm going to be in that bedroom, right? But if I'm in the 7-bedroom, you have to figure out what bedroom that is. And what is that the same as saying? Basically, which orbital, which specific of the 3 P's, which specific orbital of the 5 D's, which specific orbital of the 7 F's. Where am I? Now, I'm not going to go into the private details of what goes on in the hotel room, but I am by myself. Let's just put it that way. However, if there was someone else in the hotel room, how would you tell me apart from that person? Well, I'd be laying my head up in one bed, and then the other person would be head down because opposite spins. So you'd have to figure out which 2 electrons, of the 2 electrons, which one is me. Depends how I'm spinning. Okay, if I'm an up spin, I'd be plus 1/2. That's where the whole metaphor falls apart. I really don't like it. I need to figure out a better way to do this. So maybe next time y'all will help me with that later. I probably need to delete this whole thing before I put it online. Whatever. That's how I roll. I'm a plus 1/2 spinner. So anyway, let's go back now to I'm going to take you to the periodic table so you can see how this translates, dear God. So our principal quantum number with n refers to these energy levels, okay? Now, thinking back, I want to talk about the principal quantum number for your D's and your F's, but let's review. This block right here was called what? What's here? The S's, right? What's this block here? P's. Little old helium should be over in the S block, okay? The reason it's there is because it's got a full outer shell. It kind of has noble gas qualities, but in actuality, in terms of electrons, it should be right there. These are the D's, right? And these are the F's. So your D's and your F's, their energy level is actually below the original energy level. So this is an n-1, and this is an n-2. So this is actually level 3, 4, 5, and 6, okay? Here, the insertion is right here for these guys. So 6 minus 2 is, that's energy level 4, and that's energy level 5. Okay? So as far as the quantum numbers go, your first quantum number is just what energy level the electron falls. One thing that's important, say I'm locating the first quantum number for that. I'm not locating a quantum number for an element, not for carbon. I'm locating the quantum number for the last electron in carbon when I'm pointing to carbon. Remember, there is 1, 2, 3, 4, 5, 6 electrons in carbon. I'm only referring to the very last one when I do that. Make sense? So anywho, that number it would be for that electron would be 2. Okay? If it were here, it would be 6. If it were here, it would be 5. Got it? All right. What does the second quantum number tell us? The second quantum number tells us which sublevel, S, P, D, or F. And that's just a number. So the S happens to be 0. This is 1. This is 2. And this is 3. So N is your principal level. Azimuthal is your sublevel. So it's a 0, 1, 2, or 3. And this is technically 1 to infinity. That's the thing about Schrodinger's equation. We don't really stop at level 7. Theoretically, we can go on and on and on and on and on. The equation works like that. All right, so that's pretty easy. What about how to find what orbital I'm in? Well, that is the m sub l. How do you find it? Well, I like to do a little kind of pyramid here. There's only one orbital on any s sublevel, and it holds those 2 electrons, or these 2 electrons, or those 2 electrons, okay? So if you're in an s, meaning azimuthal quantum number of 0, that one orbital is called 0. You told me earlier there's only one s orbital. It's called 0. How many p orbitals are there? 3. You see how this is 1? To number those 3 orbitals, we go -1, 0, 1. So if the azimuthal quantum number is 1, we start numbering our orbitals -1, 0, 1. For d's, our azimuthal quantum number is 2, so how do we name our 5d orbitals? 2, -2, -1, 0, 1, and 2. So if you haven't figured it out yet, this goes from -L to positive L, based on the azimuthal quantum number. So how do I label these F's? -3, -2, -1, 0, 1, 2, and so on. So let's look at the P's real quick. We know that the S's, those are easy. This goes in one orbital, and that goes in the other orbital. The same orbital. That second electron, opposite spin, same orbital. But when we get to the P's, 1, we start -1, 0, 1, double up, -1, 0, 1. So this goes in one orbital. They each take up their own orbital, and then they double up. That was Hund's rule. Remember that? Okay? So that is what the third quantum number is. So the last thing to tell where we're at is to determine which orbital, the spin orbital, which electron are we talking about in that orbital. So if we're looking at these guys, we need to be able to differentiate between those 2 electrons. So that had to do with the plus and minus 1/2. By convention, do you remember? The first half was plus 1/2, plus 1/2, plus 1/2. Okay, and then what was the second half? Minus 1/2, minus 1/2. Why is it plus or minus? That's just how the equation goes. That's by convention. Up, 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 down, down, down. And what confuses people is the fact that when we do azimuthal is 1 and we start numbering -1, 0, 1, people want to start -1/2. First half of the block is positive 1/2. Second half of the block is -1/2. So let's put all this awesome stuff to work here. Yeah, we did all that. Pauli's exclusion principle states that no 2 electrons can have the same set of 4 quantum numbers. Where that translates to, let's say we have orbital spin diagram. Remember these? Okay. Let's say we had this. Whoops. See a problem? See how those the same spin? Same spin is what indicates that we have the same 4 quantum numbers, because these in orbital 0 both have a plus 1/2. So that would have the exact same 4 quantum numbers, right? Can't happen. Not possible. So that's how Pauli's exclusion principle translates to a picture. Not going to happen. All right. We'll do a tree diagram. So everyone has this in your notes. Let's fill this in, and then we're going to go back a slide and answer those questions. So right here, this stands for N. This is our azimuthal, and this is our M sub L. So starting with level 1, 2, 3, and 4. So what is the N? There's only one type of sublevel, and what's the name of those orbitals? It's letter S. And what's the quantum number associated with S? 0. And there's only one kind of S, and what do we call them? 0, right? So notice on level 1, there's only one sublevel called S. On level 2, there's 2 sublevels. What are they? S and P, right? Look at level 2 on the periodic table, S and P. So what's the azimuthal here? 0 and 1. The name of the one S is 0. What are the name of the P's? One is -1, 0, and 1. So these are orbitals. And remember, how many orbitals can go in each one of those? How many electrons, excuse me, can go in each one of those? 2 electrons can then go into each one of those orbitals. Okay, level 3, guess what? 3 sublevels. Wait, I don't see a D on 3, is there? There is one, right? It's next to the level 4s. So there is a sublevel 3, and so it's 0, 1, and 2. The 1s is called 0. This is -1, 0, +1, and what's this one? -2, -1, 0, 1, and 2. And level 4, how many sublevels on level 4? SPDF. Yay, that's awesome. 0, 1, 2, and 3. And we can finish filling this out. 3 is -3, -2, -1, 0, 1, 2, and 3. Now I want you to keep in mind, we don't see it, but remember, Schrodinger's equation carries us, if it carries us to level 5, we are saying how many sublevels would there be? 5. 0, 1, 2, 3, and 4. But whoa, there's no 4. Theoretically, there is. There is an orbital G out there. We just don't have any elements that we know that have those. But again, theory says that this goes on infinitely. Okay, now let's go back and answer those questions. Write a tree diagram. Done. How many orbitals make up a set of S, P, D, and F? We already did this. How many make up a sublevel of S's? 1. P's, 3. D, 5. And F's, 7. How many electrons can go into each set? So I'm going to answer number 2 down here. If I have an S orbital, how many electrons can go on that sublevel? 2 on the sublevel. 2 electrons on the sublevel. Okay? If I have, I should say sublevel. On the P sublevel, or in the P set, how many electrons? 6. How do I know that? Look at the block. Isn't the block 6, the P block 6 across? Yep. D, 10, and F, 14. Good. Now, number 3 says, how many electrons can go into each energy level? And 4 is, what's the general formula for that? So the best way to do that is just to look at your chart here. Remember, 2 electrons go into each line. So on level 1, and look at the periodic table, we can only put 2 electrons, right? On level 2, 2, 4, 6, 8 electrons. On level 3, how many is that? 2, 4, 6, 8, 10, 12, 14, 16, 18. On level 4, holy cow, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Huh. Can anyone see a relationship between the level and the number of electrons? Can we get a formula that we use N? You all know it. You learned it last year. 2n squared. Perfect. If you take the energy level and square it, multiply it by 2, that's how many electrons can go on any level. And you're going to get this. You know, for the first couple, it's easy. You can look up there and count. So level 2, I have the 2 S's and the 6 P's. Great, that's 8. That's easy. But on the AP, they might give you that theoretical level 7 or theoretical level 14 and want to know how many electrons can go on there. Well, you can't count them. You got to know your formula. Okay. What happens if I wanted a formula for just orbitals on a level, not electrons? N squared is the number of orbitals. Remember, because there's 2 electrons in each orbital. Number of orbitals on a level, all the way across, not on a sublevel, on a full level. Okay, I think y'all are getting it, maybe. Review time. All right, so let's put this to practice. Number 9, which of the following combinations of quantum numbers is allowed for an electron in a hydrogen atom? Okay, so when it says up here in a hydrogen atom, meaning the only reason that's often said is because It's just showing regular, no excited state. Don't worry. Remember, a hydrogen electron can travel all the way down to flipping radon's location. Okay, so don't let that word, just scratch it out. So we're basically looking for legitimate quantum numbers. Which sets are legit? Which can really happen? So let's start here. N equals 2, L2, M sub L 0. So let's go to level 2 on the periodic table. What does L2 mean? D's. Are there any D's on level 2? Nope. So this is no D's on level 2. Okay, the next one. N equals 3. That's the third level. Great. L equals 1. Are there P's on the 1? On level 3, excuse me? Yes. And can one of those P's be a negative 1? Absolutely. 1 could be negative 1, 0, and 1. So yay, this is good. Good set. N equals 5. Okay, level 5. L0 is what? It's S, right? Are there S's on the 5th level? Yeah. Yep. Plus 1. No. There's only one S. And what's it called? 0. So no S orbital labeled, oops, not, it is labeled 0, labeled plus 1. And the last one, 1, 0, 0. Good? Absolutely. What does that narrow us down to? What 2 electrons? The last electron in which 2? Hydrogen and helium. What did this one do? This could have been the last electron in what 2 elements? Level 3, P's. The first P is the last electron in aluminum. What would the next one possibly be in? Sulfur. So which one? We don't know. We need to know the spin. We need our 4th. Spin needed. Okay, let's go on. Do another one. How many orbitals, not electrons, orbitals are available with the following combination of quantum numbers? N equals 2, L equals 0. So N equals 2 means second level. L equals 0 means what orbital? S. So how many orbitals are in any of S orbitals on any level? There's only one orbital in a sublevel of S, no matter what level, right? So 1. How many orbitals on level 3 can have an indication of 2? What are these? 2 is D. So how many orbitals? 5, right? Any D sublevel has 5 orbitals. How many orbitals would have an L equals 3 on level 4? This is F. 7. Ooh, look there. Level 3. How many? We can do electrons. How many electrons? 2n squared, right? So that's 18 electrons. So the question's orbitals. So 9 orbitals. Could you sit there and count? Absolutely. You could say, oh, on level 3 I've got an S, I've got 3 P's, and I've got 5 D's. That's 9. That's a lot of work, though. I'd rather do this. All right. What is the maximum number of electrons in? This confuses people. A 2s subshell, that's the same as saying sublevel. How many total electrons can we put on a 2s sublevel? 2, right? In any s sublevel, no matter what level it's on, it's 2. How many electrons in a 3d? D. Oh, where's 8 coming from? 10. How about 10? N equals 4 shell. 32. Remember n, 2n squared, is the number of electrons on any level. 2p orbital. 6. No. Orbital, not sublevel. Just 2. 2 electrons only in any single orbital. If it's one orbital, it's 2 electrons. If it's a sublevel, it depends on which sublevel we're talking about. So when you're doing your homework, please be aware of the following. You get these questions that throw people off, and people are like, I don't understand. I don't get this. Whatever, I'm naming them crazy names. They'll ask you the same type of question. How many electrons can be found in the following? Blah, blah, blah. If you see this, they're talking about one single D that happens to have a really funny name. All three P's make up a sub-level. But if we're looking at electrons in just PX, or in just PY, or in just PZ, there's only two. So don't let these names scare you. They're just names of individual 2 electron holding orbitals. You're going to have to do your homework tonight to be ready for tomorrow's group quiz. I'm going to allow you to use a textbook in your group, but that's it. Those of you taking those home, textbook only, okay? No iPads. All right. So now ready for something else? Electron configuration. Haven't seen this in a while. Write the electron configuration for magnesium, krypton. We'll just do a couple of them. You guys are actually pretty good at remembering how to do this. Magnesium. All right, I'm going to let you guys do the noble gas configuration. Since this is review, second year, we're going to start. Look at the noble gas on the level before magnesium. What was that? Neon, right? Now, when we start electron configuration, we state the level. So we're looking at the next line from neon. What level is that? 3. Now you name the sublevel. Is it S, P, D, or F? We hit first. S, and how many electrons? 2. Remember this? Okay, let's try krypton then, because I think we do need the practice. So go to the noble gas on the level before it. You can't just say, oh, krypton, krypton. No, go to the noble gas on the level before it, argon. Now, what level do we start with? 4. And how many? It's S. How many electrons? 2. Now we go to the next, but wait a second. Aren't we inserting something from way below? D. So it's 3, D, 10. Okay? And now we go back to the P's, so we're back up to level 4. P, how many over to the krypton? 6. So that describes all the electrons in krypton. Be careful on the AP exam. They've been known to say, write the full configuration. And then they say, example, 1s2, 2s2, dot, 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 dot. What does that mean compared to what's different than what I just did? You can't start. Please watch the instructions. So on the AP, and when they do tell you to do the full, they're never as far down as like radon or anything crazy. So if it were a krypton, we'd have to go 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d10, 4p6. Okay? So do know that you might have to do the full. I will never require you to do the full, though. These are called core electrons. Core electrons aren't that important because they're not going to be messing in our bonding. Okay? All our bonding electrons and electrons that are transferred for charged ions and things are all the ones beyond the noble gas configuration. All right, one more. Let's do bismuth, and we'll do it shortcut. So we go to the noble gas before, which is what? Xenon. And we start level 6. Uh-oh. 6s2, then what? 4f14, then back up 1. Uh-huh. Oh, it's 3. Sorry. Yeah, I was thinking noble gas. I had noble gas on the brain. 6p3. Good. Doing okay? All right. Now, along with this, I'm going to revisit how to do an orbital diagram, also known as a spin diagram. Okay? And you're going to learn the term para or diamagnetic in the process. So, silicon. Before you do any spin diagram, let's quickly do the electron configuration, the noble gas electron configuration. And silicon, why can't I Oh, there it is. All right, starting with the noble gas before is neon. And then we go, is that 3, guys? I can't. Okay, 3s2, 3p2. When you're drawing these, I'm not going to require you to draw anything in the noble gas area. You're only going to draw beyond. So we're going to draw boxes to represent the orbitals. How many s orbitals are on any sublevel? Just one. So we draw one box, and we're going to label it 3s underneath because it's a 3s orbital. And then how many in a p sublevel? 3. And we're going to label it 3p. Then I'm going to fill in my electrons based on how many are there. So if I've got 2 in the 3s, how are they going to be placed? Up and down. You can draw your full arrow if you want, whatever, I don't care. I'm lazy, so I just do the little half arrows. And then P, I've got to place 2. Am I going to go up, down in the same box? No, I'm going to follow Hun's rule, the bus rule, the New York subway rule that people don't follow. I get so mad. I'm sitting there, the car's empty. Some scary homeless person comes and sits like right next to me asking me for money. I'm like, get away. Now I sound like a horrible Westlake person. It's not that I don't like scary homeless people. I just don't want to sit next to them. And I will give them money. Just don't go sit behind me in another seat. So anyway, that's just the rule. To sit, go into separate, and then double up. All right? Let's do one more I'm going to add on. Let's do, I don't know, bromine. On the noble gas before is argon. And then we're at 4s2. 3d10, 4p7. No, 4p5. Can't do 4p7. How do I know that? Because it's a p and there's only 6 and I'm 1 away from the size. It has to be 5. All right, so again, I'm going to draw an S box. I'm going to draw a D sublevel. Uh-oh, how many in that one? Okay, and then I'm going to draw my P's. And I will talk about paramagnetic here in a minute, which I failed to. S, all my D's, up, 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 down, 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 and then 5 P's. How am I going to place them? Up, 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 down, down. I'm going to put my 5 P's there. So what's with this para or diamagnetic? Any unpaired, if there are unpaired electrons at all, it is going to be paramagnetic. These are the dudes that will either be ions with color. If you're curious as to an ion being colored or not, if the ion has unpaired electrons, it will probably be colored in solution. It's also the stuff that has magnetism. Okay, things that are paramagnetic can allow other things to come in and kind of share an orbital space. So if I had another thing with similar but opposite spacing, they could come in, share for a while, and come out, and that's what makes some things magnetic. Things that are diamagnetic are not going to show magnetism. And in a diamagnetic species, everything is paired. So without me drawing, what things would always be paired? Noble gases. What else? The end of every block, right? Wouldn't the end of every block be diamagnetic? Because there would be no unpaired. To be paramagnetic, any 1 electron, 2 electrons, 3, it doesn't matter how many. If any of them are unpaired, they're going to be paramagnetic. Okay? All right. This is an exception. And this happens all the way down the copper and chromium family. And this only happens between the S to D jump. So this is number 14. All right, so for now, chromium. Give me the expected electron configuration for chromium. So chromium would be argon, and then 4s2, 3d what? 3d what? 4, right? Okay, let me show you what's going on here. So we have an S. We've got our D's. 5. I need 5 boxes. Looking at this, I've got, here's the situation. 4s, and in terms of energy, if I really were drawing this correctly, The fact that it's 3 instead of 4, what does that mean? It's a little bit closer to where? The nucleus. Okay, so really, we're a little bit closer to the nucleus here. Okay, and we are also, the thing about S's and D's, they are super close in energy. It's kind of like me jumping down a step from here to here. Okay, so why would this electron then, which is what really happens, move to here? Now, I heard last period some people gave me the can statement. Go ahead. Go.
Because it's stronger if it's half.
Okay, stable. That's correct. Half-filled orbitals are more stable, but that's not an acceptable reason on the AP exam because it's not a reason. Why are half-filled orbitals more stable than filled orbitals? Why would this little electron be happier here than there? What do you think? Tell me about electrons. What's their charge? Well, it's closer to the nucleus, but that's not why it would be more stable. Any half-filled orbital. Why? Not bonding.
Because it's negative and it wants to go to the positive.
Tell me about all electrons. What's the same about all electrons? Negative charge. What can you tell me about like charges? They're repelling. So what happens here, yeah, electrons share orbitals all the time. However, with a little bit of energy change, actually bringing it a tad bit closer to the nucleus, you can give up these repelling forces there. No more repelling forces. And, hey, I'm closer to the nucleus, a smidge. This jump will not happen, though, from S to P. It's too big of an energy differential. And there's really no advantage to it either. It loses energy by having to get over to the P's, plus it's not closer to the nucleus. Here, this is all good. So this is the ground state configuration then. AR, 4s1, 3d5. And it only happens for chromium, molybdenum, and tungsten down in the chromium group. Now, why does it happen in the copper group? Same kind of reason. Look at the copper. We've got AR, 4s2, 3d9. Well, it's not that. The ground state is actually 4s1, 3d10. Why? Well, won't it have repulsive forces in that last D? Yeah, it does. So why does it do it, though, still? Still a little bit closer to the nucleus. Got it? So those are just exceptions to the electron configuration. They do show up on the AP exam quite a bit. All right, last thing is charged ions. These are fun. Sulfur. Let's just do sulfur without its charge. It's neon. 3s2, 3p4. Whoops. 3s2, 3p4. Well, if sulfur wants to become a -2, what has to happen? It's going to gain how many electrons? 2. So it's actually 3s2, 3p6. Easy, right? Aluminum. Aluminum, just look at the periodic table and do it. Aluminum would be neon, but 2. Well, actually, I need to show you. So aluminum alone is neon 3s2, 3p1, right? So how is it going to become +3? It's going to lose 3, right? Isn't that all its valence electrons? So now it's actually 1s2, 2s2, 2p6. Okay. I'm not going to leave neon in parentheses. I can't do that for electron configuration. That's an easy positive charge. Where it gets kind of tricky, let's look at Fe+3. Iron, its normal configuration is argon, and then what? 4s2, and then 3d, no, not 6, is it? I guess it is. 1, 2, 3, 4, no, 3d5. Okay. Now, for it to become +3, it has to lose 3 electrons. This is where you have to be careful. Be very, very careful. Do we know what the term valence electrons mean? Valence, outermost. What are the outermost electrons here? The S's. So it's going to lose its S first, right? And then lose one of those. So it's going to be argon 3D4 because of the level 4 in front of it. Let's do one more of those. Let's say I want to do, we know antimony, right? It can be what two charges? Nope. 3, 5, right? So let's figure out where its charges are coming from. Antimony is normally krypton, and then 5s2, geez Louise, 5s2, 4d10, 5p what? 1, 2, 3, right? 5p3. We know that antimony can be +3 or +5. So 4 is not going. It's not going to lose any of those. Now +3, this is going to go away, obviously, right? But where is it going to get the 2 for +5? Those two. Okay. So always the biggest mistake on the AP exam that I saw when students were doing this, they were just looking at the periodic table and plucking them off really fast. Like aluminum, it's easy. Pluck, pluck, pluck. It's neon now. Aluminum +3. Take away 3, pluck, 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 it's neon. That doesn't work for something like iron because you don't lose the D's. First you lose the S, and then you lose the D's if there's nothing left on the S or the P. Okay. Let me just pause. I'm not going to do 17 or 16 today. I'll do it right before your quiz tomorrow to refresh. What I do want to do really quick is talk about these excited states. There are exceptions. Hund's rule is an excited state, and so is the Aufbau principle. You can put in energy and make funny things happen to the electrons. When electrons don't fill an order, say you go to an S and you don't fill your S, but then you're filling P's all of a sudden, that's a violation of the Aufbau principle. Violating Hund's rule is an excited state where you don't do the up, 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 down, down, down in a row, in a set, in a sublevel like of S's and P's. The bus rule, okay? Pauli's exclusion we've already talked about. It's in the box. If we have 2 ups in the same box, that's impossible. It's not an excited state. It's impossible. Excited states can happen, but they're real unstable, and the electrons will fall back to where they were and give off energy. So let's go ahead and predict some of these excited states real quick. How does this first one look? Is that excited, or is this a ground state? That looks good to me. Ground. No violation. What about the next one? Uh-oh. That's excited. And it's what violation? Nope. Hund's Aufbau is it's not filling an order. We're filling an order within the same sublevels with an order. We're just not putting up, 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 and then doubling up. This one, uh-oh. This is impossible Pauli. Right? Because those have the 2 same quantum numbers. What about this one? It's excited Hund's. Okay, next one. Uh-oh. Pauli, impossible. Okay, this next one. This is ground. No, it is ground. It is ground, though. Why? Because it's the exception. Isn't that the chromium? Chromium? Yep. But you were right thinking, when someone said Aufbau, you kind of were right, because this would be excited Aufbau. We're not filling in the right order. But remember, that whole exception doesn't occur between the S and P's. It only happens for that little S to D jump. And then this last one, excited Hund's. When I say excited, I could take a beam of light, shoot it at an atom, and create this little jump from here to here. This electron would not be stable, and it would fall back pretty quickly, but it can happen. Unlike the Pauli thing, that just can't happen. All right, ladies and germs, that is it for the day.